Hello everyone. Now we are going to start the second part of our relational data models. So in this set of slides and in this particular lecture, we are going to extend our relational data model, the one which I covered in the previous set of lectures, to something which is called as a bag model. You may remember that in my previous videos, when I was talking about relational data models, we made an assumption that all our relations slash tables, whatever you want to call, we assumed that they were sets, right? They were sets of tuples. In other words, a tuple cannot repeat in a relation, right? So that's the set model, right? So in these set of slides, what we are going to do is that we are going to extend that algebra to the non-set model, or more precisely what we call as bags. Okay, and why we are doing this? We are doing this because in real life, when you are working with tables and all that, it's hard to work with the set model. It's too constrained, right? In reality, until unless you define something called as primary key and all that, right? In some cases it's hard to maintain the set property across all relations. So for example, one of the uh, biggest change that comes in the operators is in the operator of projection. Recall that after you do a projection, in that pi operator, you had to do one more task of removing the duplicates, right? Something like that is it's time consuming and all that. So people extended the relational algebra to bag model, right? Okay, we'll see how it goes. Okay, so relational algebra on bags. So a bag or a multi-set is like a set, but an element can appear more than once. So we have some examples here. So this first example, 1, 2, 1, 3. So here the element 1 appears more than 1, right? So this is what is called as a bag. Right? So and in the second case, 1, 2, 3. So this is a set, and it also sort of satisfy the definition of a bag, because a set can be a bag, but a bag cannot be a set. So that's the way to remember it. Okay, so as I said before, the reason we are trying to study the bag model is because the SQL, which is one of the most prominent query language for relational databases, this is actually a bag language, and another primary reason is because operators like projection and all, uh, they are much more efficient when you consider bag model than set model, right? So that's the reason why we are trying to study the bag model of relational algebra. Okay, so now what we are going to do in the next couple of slides is that we are going to revisit all our traditional relational algebra operators and then see how that how those operators change when you are having bags instead of sets, right? So the first one, select operator. So select operator, there's really not much change, because remember, whenever we had that sigma operator, the way a sigma operator was executed is that conceptually you would loop through every tuple, and then you check whether in that tuple, whatever the condition that you want to check, is it satisfying or not. If it is satisfying, that particular tuple is given out, right? So the selection operator pretty much changes, pretty much remains the same, sorry. Projection operator changes significantly. As I said before, in our relational model on set, after we took a projection operator on a column, we used to have an additional step of removing the duplicates. But now we don't have that anymore, right? So given a relation, if you pass it through the projection operator, it will take out one column or more than one column, whatever it is, and then it will just give that as a relation, right? And that, as you can clearly expect, that you'll have duplicates. Okay, and products and joins will show you how how these things work. I think I have some couple of examples here. Okay. So bag selection. So you have a relation here, right? And I'm passing this particular relation R through the following select operator, and my condition is that I'm going to output all the tuples where the value, the sum of the values in column A and B is less than 5, right? So I'm going to loop over all tuples of relation R, and for every tuple I'm going to check this particular condition, right? So I think in this particular example, the first tuple and the last tuple, they satisfy this particular condition, So therefore, so sigma A plus B less than 5 of R is this particular relation. Remember that even in the bag model, the fundamental concept of relational operators taking in one relation and throwing out another relation, that still remains put, right? So here the only thing we are doing is that we are changing the definition of what is a relation. Previously we said that relation is a set where no tuples, no two tuples should be identically same, but now we are sort of relaxing it, for ease of implementation of these things, right? So both this guy and this guy are a valid relation as per the bag model, but in our set, this would not have been the case. Okay. Okay. Right. Okay. So the projection operator. So we have this relation R, the two tuples are so same here, and then I take an projection on the column A, right? So the output in bag model is that I simply take all the tuples of relation R and throw out whatever was the value of the attribute A. Right? So this is the output of pi operator on an bag model relation, bag model of relation. Okay. So cross product. Conceptually, cross product remains the same. Now, the only thing that you have to take care is that when you are conducting the cross product, you have to consider both the copies of the tuple. So here the tuple 1 and 2 appears twice, right? So now when you are computing R cross S, both these tuples will join with both the tuples of the relation S, right? So therefore 1, 2, 3, 4 and 1, 2, 7, 8, they appear twice in this final relation R cross S, right? And the 5 and 6, this particular tuple, it will join with both of these to create these two tuples. So this is same. The only difference to note is that both the copies of the tuple 1 and 2, they are going to join with both the tuples of S when you are doing R cross S. Okay. Let's see. Okay. Next is theta join, right? So similar case over here. You have two relations R and S. R has some duplicate tuples, and you want to join R and S on the following theta condition. It says that R dot B should be less than S dot B, right? So again, conceptually, what we will do, we'll take the first tuple here and we'll try to join with both of these tuples, right? So this tuple, as per this particular join condition, it will join with both these, right? So that's why it came here. The 5, 6 tuple, this tuple will join with only the second tuple of relation S, so only one tuple over here. And then again the second copy here, this 1, 2, this tuple also is going to join with both the tuples of S, right? So we get last two tuples like this, right? So this is bag theta join. Okay, bag union. So here, what we are going to do is that we have two bags, 1, 2, 1 and 1, 1, 2, 3, 1, right? So one is appearing multiple times, 2 is appearing twice, and all that. When you perform a union over bags, what you are going to do is that you are going to keep all the duplicates also in the final result. So one is appearing, I think, 5 times here, 2 is appearing twice, and 3 is appearing just once, right? So this is called as bag union. Okay. Next, bag intersection. Okay. So here, there is a small caveat, to consider it. So consider these two bags here, 1 2 1 1 and 1 2 1 3. Right? So 2 is appearing only once. So you take this intersection. So 2 comes here straightforward. 3 is not there. So we don't even need to bother. Now the element 1, it is appearing thrice in this set and it is appearing twice in this set, right? So now what we're going to do is that when we are taking intersection, we try to take the minimum. It's as if that both these copies of 1, see how many copies of 1 are there on the left side, and whichever is the minimum number, that guy comes here. So for example, if this had 2 copies and this had only 1 copy of 1, then in the final result of this intersection I'll have only 1 comma 2. Okay. So something, if I had something like this, right? So if this was my input, then my output would have been this. Okay. So that's the way to remember, whichever set has the smaller number of the copies, that makes it to the final output. Okay. Next slide. Bag difference. Okay. Bag difference also, there's a small caveat, right? So recall that in the difference operator, when you were studying with the set model, I said that a minus b is equal, it will contain all the elements of a which are not uh, available in set B. Right? So now when you have bags, the way to think about is that let's say you have these two bags, 1 2 1 1 and 1 2 3. So the way to see is that each element of this bag 3, a bag B, will try to knock off elements from here to see which ones finally remain, right? So this one copy of 1 will knock off one copy of these element 1s over here. So this guy will knock off this 2 will knock off this. So there is no 3 over here, so this is ignored. Okay, so that's the way to see. So therefore this set minus this set is equal to 1 comma 1. Now if I had one more copy of 1 over here on in the set B, then both these ones, the two copies of ones over here will knock off two copies of ones over here, and then the final output would have been just this. Okay, just to illustrate. Hope this is clear. Okay. So one thing to note is that loss on bag model, they are not same as the set loss. Some carry forward to bags also, but others don't carry forward. So as an example, the union operator carry forwards. The commutative law of the union, which means that R union S is equal to S union R. This holds for the bags. But just to give you an example, there is an idempotent rule which says that S union S. So this is the set law. Now if S was indeed a set, then S union S is equal to S. But if S were a bag, then S union S will not be equal to S, because you may recall that under bag model, when you're performing union operation, you take all the duplicates with you to the final result, right? So 1 union 1 is equal to 1 comma 1, which is not equal to 1, right? So just just in note that we have to be careful that all our set laws do not carry forward to the bag model, right? Some carry forward, but not all. Okay. Okay. So we have three new operators of interest to us. The first one is delta, which says that it is used to remove duplicates from bags, tau to sort some tuples, and gamma for grouping and aggregation. So we are going to stress on this particular operator a lot more than the other ones, because this is extremely important. Right? So pay specific attention to when we are covering this grouping operator. And last but not the least, we have this concept of outer join. So outer join avoid something called as dangling tuples. So dangling tuples are the tuples in a relation which do not join with any other tuple on the on the next relation, right? So in outer join, what we happens is that tuples which do not join with anybody else, they are also padded into the relation by putting appropriate null values. We'll see an example of outer join. But out of these four, as I said, grouping operator is perhaps the most important operator. Pay specific attention to this particular portion. Okay, so let's quickly see. Uh, so duplicate elimination, pretty straightforward. You have a relation R2, which is a bag. That means you can have some copies. You pass it through delta, you get another relation which where the duplicates are removed. Right? So straightforward. Yeah, just a small example. I think this is self-explanatory. Okay. Sorting. So sorting, the way we do it is that let's say you have a relation R2, you pass it through this tau operator, and L is the list of attributes, right? So now what we are going to do is that if you have multiple attributes, then this particular R2 relation is going to be sorted on the first attribute, and then for tuples where they are the first attribute is same, we use the second attribute, and so on. Okay, so next we have aggregation operators. So aggregation operators are not technically part of the relational algebra, but they are very widely used, right? So let me just give you an example. So aggregation operator, the way they work is that they work on columns, right? So for example, you have a relation like this. You can say that you return the sum of all the values which appear in the column A, right? So that is sum A. Similarly, you can write count A, which returns the number of tuples and so on. Similarly, max, average, and all that, right? So we are talking it in the relational algebra, but these things, they matter. They are dependent heavily on the SQL or the database vendor which implement them. So for example, this count A, right? So here I said that it is returning the tuples, but in some implementation, if you have null values here, so then this count A can just return the number of non-null values which are seen in that column. Similarly, the average, depending on the implementation, the average may take the null values, the count of the null values, or it may not take, right? So those kind of things, they are dependent heavily on the vendor who is providing you the database. But more or less, I hope you understand the concept, right? That all these aggregation operators, they are applied on the column. So aggregation operators by itself, they are okay, but they have a lot more power when you consider them along with the grouping operator. So grouping operator, as I said before, it's an very important operator, and let's try to focus on this. Okay, so the way we write grouping operator is that we have a relation R2, we write gamma, and we write the L, right? So L is a list of attributes in our relation R2, and that list can contain only one of the following two types. So either it can be something called as the individual grouping attribute. So that means you are grouping the tuples of relation R2 on those attributes, or it can be one of the aggregation attributes, right? So you are not allowed to have any other thing in this list L. So let's take an example here. Okay. I think it's best that we go to an example. Okay, so we have an relation here R. Okay. Okay, so let's see this relation here. It has three columns and three tuples, and I'm writing something like this: gamma a comma b, and then average c, and this average over c, I'm renaming it as x. This is what we are doing. Right? So now, how does this work? So the way to think about is that whenever you see an expression like this, so you first forget about all the columns which are listed inside the aggregation operator, right? So instead of average, it was written like max or min, or if I had several columns here, right, and I had written something else for them, right? So you forget about them. So you first see only the attributes which are not inside an aggregation operator, right? So A and B are not inside aggregation operator. Now what we are going to do is that we have two steps. So in the first step, we actually see all the unique values of the pair AB which appear in my relation, right? So now I think in this particular relation, the pair AB has two unique values. So one is this 1 and 2, and the second unique value is 4 and 5. If I had something like 1 and 3 tuple over here, then the AB would have three unique values. So 1 and 2, 4, 5, and 1, 3. Right? Now, what we do is that after we determine the unique values of, if I had more attributes over here, and if I had written something like this, A, B, and then maybe something else also, right? So, whatever attributes that are listed over here, you take them as one entity or something like that. You take them as one, and you determine the unique values which that group shows across all the tuples of your relation, right? So here I had two attributes A and B. So I'll go through my entire relation, and then I'm going to see how many unique values does the pair AB have. It's not A and B that you're going to see it separately, right? So if you have two attributes here, so you have to see the unique values that the particular pair shows in your relation. Okay, so here A and B shows two unique values. 1 and 2 is the first unique value, and 4 and 5 is the second unique value, right? So now after you determine the unique values, what we do is that internally we group all the tuples below these unique values. So first unique value is 1, 2. So you list all the tuples where the value of A and B happens to be 1, 2. Second unique value is 4, 5. So you list all the tuples from your relation R where where the attributes A and B have the value 4 and 5, right? So that is called as the grouping of tuples as per the unique values of the pair AB. Now after you group these tuples, then the second thing comes. Now the end of the grouping operation is always going to be one tuple per group. That be it relational algebra in this case, or when you even go to the SQL, the gold standard, or you can take it as the word of the Bible, that each group, after the grouping operation is done, each group presents only one tuple to the final result. That's the fundamental requirement, right? So here the AB, when it had the value 1, 2, this group contained two tuples. So that's why these are shown in green. So each group I think is one color. Yeah. So 4, 5, the second unique value, that's the second group, and it has only one tuple here, so fine. But if we had another, let's say 4, 5, and then 8 over here, then I would have written 4, 5, and 8 in the red. Right? So we perform the groups, and in the second stage, we have to return one tuple per group, right? So you take the green group, and now you have to return one tuple from this group. Now how do you do that? That is where all of this aggregation things come into picture. If you don't write aggregation anything like this, what I would return is that if I just had written gamma AB R, then my result would have been just two tuples, 1, 2, 4, 5. That's all. Now, if I had returned, if I'm writing things like here average C and all that. Now what we do is that after the grouping, I'll take the C column and I'll take the average of 3 and 5 and return here. Similarly, I'll take the second group 4 and 5. So there's only one tuple here, so average of 6 is 6, right? So that is where this aggregation operator comes. Again, just repeating that whatever attributes are sitting in the non-aggregation part of your grouping operator, you group all the tuples according to the unique values that that these things will take, and then inside a group you perform the aggregation operations. And the golden rule is that always one tuple per group. If you don't have any aggregation operators, then just the unique values which these columns A and B will take, just those will be written in the result. If you put any aggregation operators average C, then inside a group, inside a particular value that these things take, you perform the aggregation operation and return it, right? So so listen to this part of the video, maybe once more, just to make sure that you understand it. Okay, it's a key concept. Yeah, outer join. I think I can just take it with an example here. Okay, so we have two relations, A and B, right? And I want to join R outer join S, right? I think this is doing natural join. So what happens is that this tuple 1 comma 2, it will join with only one tuple here as per the natural join, right? So when you write R outer join S, if you write R natural join S, you would have received only one tuple, right? But when you write R outer join S, then what is happening is that it will list tuples from the both relation R and S with padding nulls from the other side, right? So for example, this guy had 4, 5 and it did not have any matching from the S relation. So I would write 4, 5 and null here. And similarly, from the relation S6, 7, this guy did not match with anybody on the relation R side. So I write 6, 7 here and then null here, right? So this is called as R outer join S. So when you go to SQL, there are other commands, there's something called as left outer join and right outer join. So in the left outer join, what happens is that tuples from R which do not join with S, they are returned by padding nulls for the corresponding on the S part. And if you had done R right outer join S, then the tuples from the S are all shown, and and with padding nulls for the tuples where there is no match, right? So these are the details in the SQL part, right? So this is the concept of R outer join S. Now what we are going to do is that I'll cover one example for grouping operator, and right, so that you understand it nicely. Okay, so let's take this example here. So in this schema, there are just two tables, classes and ships. So class is like a blueprint. So you have class name, you have something called as type, the country which released that class, number of guns, bore of uh, bore of that particular gun barrel which is there on that class of ships, something called as displacement and the ships. So what happens is that class, the tuples in this classes relation, they are more like a blueprint, as I said, right? And then ships are actually, you take a class, the quote unquote the blueprint of that, and then you construct a ship out of it, and then you release that ship, right? So therefore, in the ships table, you have the name of the ship and the class to which this particular ship belongs, and the year in which it was launched. Okay, so this is the relation between classes and ships. Okay, So let's try to see an relational algebra expression. Okay, let's see this. So here the query is that we want a relational algebra expression to which gives all the unique bores of the ship, not the classes. It means I need the unique values which this particular this particular bore column contains, and for each unique value of the bore I want to find the number of ships which are having that particular value of bore, right? So recall that this particular table, classes table, does not have information on which ships were constructed out of this class, but whereas we actually want the number of ships which are there, right? So the answer for this particular query cannot come from just one table. It has to come from two relations. So the way we are going to model it is that first I am going to simply join my classes and the ships table on this particular attribute, class attribute, because this is the only way in which we can join. So now after joining these two, what you have is that for every ship you sort of assume that you have details of all of its class, right? So for example there is a ship called Vikrant, right? And the class is some class, and so for the tuple Vikrant, and let's say it was launched in year 2000, I have, and along with this I have all the details of the class of this particular ship, right? And similarly there can be another ship Vikram, and that ship may also come from the same class. So there also we have after the join operation. So in short, after this first step, what we have is that we have for every ship we have details on its class, right? Because we have R1 is nothing but the result of the natural join between classes and ships. Now, in this particular temporary relation R1, if you compute an aggregation on the column bore, what will you do? Now, what will this operator do? First, it will take all the unique values of the bore which are there, right? And for each unique value of bore, it will collect all the tuples. Let's say the bore value is 20 mm. So for 20 mm, it will go through all the tuples over here, and it will see which tuples have the bore value of 20 mm. Let's say the another unique value of bore is 30 mm. Then again I will go through all the tuples of this relation and then and take out all the tuples where the bore value is 30 mm and so on, right? So if the bore column had 10 unique values, I'll create 10 groups, and in each group I'll have all the tuples from my relation R1 where that unique value of bore was seen, right? So now you have the first part, right? I have I have computed all the unique bores, and for each unique bore I have collected all the ships which have that bore value. Now all we need to do is perform an aggregation operation on that each of the groups, because you remember that this gamma operator is going to return only one tuple per group, right? So if I had 10 unique values of the bore, I'll get only 10 tuples in my final result, and with each unique value, for with each tuple I have to return the number of ships which has that unique value. Now, how do I do that? I put the count aggregation operator, right? So this aggregation operator is going to be conducted once for every group or once for every unique value of bore, right? And that is returned as the ship count, right? Again, take your time, debate. If you have any doubts, get back to me. It's very important that you understand how this gamma operator is working, because if you don't understand here, the same thing is going to get repeated in the when we go to the SQL part, you have a group by operator there also. Okay? The same mistake will continue. Okay. Okay, good. Let me stop here.